I want you to consider today is this function, y equals e to the negative x squared. Now that function looks like this. So this is the function. It's positive. It's also even. Even means it has y-axis symmetry. This is used in statistics, physics, and other STEM places. And what we're interested in doing is we are interested in finding the area under that curve. So the area under that curve can be gotten by an integral from negative infinity to infinity e to the negative x squared dx. And you try to do a u substitution or any of that other stuff, you're going to end up getting a headache. Yeah, that's what you're going to get. Okay, so what I want to do, because this is even, I'm going to write this as 2 times the integral from 0 to infinity e to the negative x squared dx. That's what that is. And that's still a really hard integral to do. So what I'm going to consider is squaring it. Square I. And what you end up getting is you get 2 copies of this. 2 integral from 0 to infinity e to the negative x squared dx multiplied by 2 times integral 0 to infinity. I'm going to change the letters out. It's not going to make a difference. E to the negative y squared dy. Okay, so that's what I'm doing now. I'm going to go ahead and say 2 times 2 is 4. I'm also going to bring this, because it doesn't have any x's in it, I'm going to bring it in to that integral. It's kind of like a constant. So I have integral from 0 to infinity, integral from 0 to infinity e to the negative y squared dy, e to the negative x squared dx. Okay, the next thing I want to do is bring that in. And now I have 4 integral from 0 to infinity, integral from 0 to infinity, e to the negative x squared minus y squared dy dx. This right here is a 2-variable function, and so we're doing a double integral. And we're integrating over this region right here. We're integrating over from 0 to infinity, 0 to infinity. We are integrating over quadrant 1. So the function is flying above that, and you're integrating. You're finding a double integral now. And when you have a double integral, you can go polar, which means I'm going to change this to polar coordinates. This is 4 times the integral from theta goes from 0 to 90 degrees, or that would be pi halves. And then r goes from 0, well, to infinity. This is e to the negative quantity x squared plus y squared. That's actually negative r squared. And you do your substitution correctly, you have r dr d theta. Now we can do a u substitution on that. And we end up getting, let's bring it up here, 4 times the integral from 0 to pi halves sorry, u substitution is going to make it so we would, and I'm eyeballing this, e to the negative r squared over negative 2. This gets evaluated from 0 to infinity, and then we have a d theta here. Now we continue. You put infinity in there, because it's e to the negative r squared, that's going to get a 0. You put a 0 in for r, you will get a 1/2. 4 times the integral 0 to pi halves over the constant 1/2 d theta. Well, you can easily see that that's going to be 1/2 times pi halves. So pi halves times 1/2. Well, after everything's reduced, you end up getting I squared equals pi. Now that's not what we originally wanted. We wanted the area under the curve. We wanted just I. So what I'm going to do is take the square root, take the positive part. We have I equals the square root of pi. Excuse me. It's beautiful. This is beautiful.